The next notebook, called Notebook 1, within the Mirroring LRS folder, essentially takes the raw uncalibrated images that are downlinked from the spacecraft, all the way to the white light curve, which is the time series data set that we're interested in when analyzing exoplanet time series observations. And this is true not just for mirroring, but for all the instruments on JWST. So for those of you who are following along with the notebook, this is designed to be able to run end-to-end in a single click. But for the sake of this webinar, I'm going to be walking through the stages one by one and giving some explanations for the exact processes that are happening at each stage. All right, so the first step here is just basic setup for the run. So you're going to have to import Eureka, which is the main package that I'll be using to process all this data. This is a very, very important code, especially for exoplanet time series observations with a number of instruments. So we're just going to run this cell, right, to import some of the basic packages. Now, for file names, you're going to need something called event label, which basically identifies what type of run this is. So being a MIRI LRS dataset, the event label here that I've chosen will be MIRI _LRS. This will appear in all the directories that are produced by this pipeline. Okay, so having established an event label, you're going to have to point the pipeline to the location of your data. So in this case, I've made a change to my local directory where I've held all the data products from this pipeline run for people running locally or on the server. You're going to have to manually set this as well. So this will be the location, the upper directory for all of your data products. Now, this notebook is designed to be able to process all stages of Eureka, but for the sake of brevity during this webinar, I'm going to skip the run. The reason for this is that this stage usually takes the longest, and the time it takes depends on your machine, the number of cores you're using on the machine, as well as the type of observation, the length of the integrations within the data set. So to skip the step and use the cached files that you've either manually downloaded beforehand or using the ones on the server, you can set this to true, which is what I'm doing here. Okay, so even though I'm not going to be running through running the stage one pipeline, I want to just explain what happens here. So stage one of Eureka is essentially a wrapper around the first stage of the official JWST calibration pipeline maintained by Space Telescope Science Institute. So as I mentioned, this step takes the raw and calibrated data, which are consisting of non-destructive reads of the detector, and converting them, essentially collapsing them into individual integrations where the raw data count numbers are converted to count rate. And this is sort of the basic unit of flux that will be used typically for time series observations. So there's extensive documentation on the JDocs website explaining all the various details of the steps comprising the stage one pipeline. But here are some toggles that you can use within Eureka to help customize perhaps the way you're running this pipeline. So how Eureka functions is that each stage is fed what is called a Eureka control file. You can see it basically written out here. It's essentially a plain text call script that establishes all the custom parameter settings that you want to use for that particular stage. And each stage of the Eureka pipeline will have its own ECF. So here, just kind of basically, the main toggles that you are interested in for stage one are turning on or off the various pipeline stages. So this is a list of the basic pipeline stages that are run as part of stage one of the calibration pipeline. And you're allowed to set these skip parameters to true or false to customize the particular way you want Eureka to run the JWST calibration pipeline in stage one. Now, most of these settings that you see here are relatively default. These are sort of the best methods that typically will allow you to get good data. So you probably don't have to experiment with too many of these. But in case you're wondering, in the notebook, there's an explanation for what these do. In the case of MIRI detectors, there are various persistence effects as well as readout effects affect the first frame and last frame of each integration. So by default, the first frame is removed during the processing. It removes some amount of the persistence at the beginning of each integration. Likewise, the last frame is by default removed. That is, skip last frame equals false in this case, which instructs the pipeline to remove the very last read. And the reason why you want to do that is, in the case of MIRI data, the last read is simultaneous to the readout, in which, and what we are finding is that there's a systematically different behavior in that very last segment of the integration, which affects the ultimate count rate measurement in somewhat of an unpredictable way. So by default, for TSOs that are, that is time series observations done with MIRI, both these steps are not skipped. That is, skip first frame, skip last frame are false. Some other interesting things to keep in mind is that MIRI subarrays are affected by what is called the electromagnetic interference noise, which is essentially an interference pattern that is imprinted on the data. So if you look at the raw images, you will often see this striping, this horizontal striping that is the manifestation of this interference effect. Now, the official pipeline has various ways of correcting for this, and they have relatively different performance when it comes to TSOs. So the default is to actually, if you run the JWST pipeline officially, this will be run. The EMI correction step will be run. But in the case of Eureka, what we're going to do is we're actually going to skip this. What we're going to do instead is to account for this EMI noise later in the pipeline processing workflow. So I won't get into too many of the other details. Feel free to read through the descriptions here. There's, of course, a lot more detailed descriptions on the JWST pipeline documentation pages. But suffice to say that this setting that you see here in the ECF file on the notebook is relatively standard and should work for most TSOs. So this step, as I mentioned, is the longest in time. In my case, I'm running M3 Mac with Sonoma, and it took me about 5 minutes to run the 6 uncalibrated data sets that are part of this workbook. So I'm just going to skip these steps and proceed to the next stage of the Eureka pipeline, which takes as input the outputs of this stage. So just to illustrate, what you will find is if you run this pipeline on your machine or on the server, you'll see a directory that is automatically made by Eureka. It has the date of your run, as well as event label that you set, and then a sequential run number in case you run multiple runs within the same day. So the output of the stage 1 portion of the pipeline is something that looks like this. For each segment of the light curve, you will produce a rate file, which you're not going to be using because it's a TSO, and also a rate ints file, which stores the individual integrations, the individual time steps of the time series as individual count rate images. And this is what you're going to be used as the input to the next stage of the pipeline. For those who are using cached files, you'll see a set of rate ints files in your directory. Okay, so let's proceed to the next stage. Next stage is relatively short. This is corresponding to stage 2 of the official JWST calibration pipeline. And once again, the Eureka functionality here is largely as a wrapper around this official calibration workflow. So for TSO data, generally, there's actually very little in this stage that we're interested in because most of our work is going to be done in relative flux units. So we're not as, we don't care as much about the absolute flux. So what this means is that generally when running Eureka, you will have the photometric calibration step and the pipeline internal extract 1D spectral extraction step turned off. So skip photon, skip extract 1D set to true. This saves a lot of time. And otherwise, we won't be using the data sets that are produced, the outputs are produced by those steps. So the only two steps that are typically important for TSOs is the first step, which is not optional. This is assign WCS. In short, this is in charge of populating the wavelength grid, the wavelength solution that will be used to extract the spectrum. So basically establishing what wavelength corresponds to each row on the detector. And then the next step is flat fielding. So this corrects for different sensitivity across the detector, as well as other effects of the detector that are important for normalizing the response across the image. Now, typically you want to not skip this step. You want to do this step to correct for these changes. But in practice, you can also experiment with skipping this. In practice, the source is relatively stable across the time series on the detector, so the pixel-to-pixel sensitivity variations are usually a minor effect. But for the sake of this demonstration, we will in fact run this flat field step. Here you can see that flat field skip is set to false. All right, so without further ado, let's just run this step live. So first, we have to run the cell that populates the ECF file for this stage. And having done that, we can then just run this stage 2 of the Eureka pipeline. It should take less than a minute for sure, but probably something like 20 to 30 seconds. So there's this extensive logging that is output to the notebook. And in this case, we are choosing to also save these log information in a separate file. So shortly, now that it's finished, we can see that now in our directory, this new stage 2 folder has been generated by the pipeline. You see a subdirectory that, again, gives you the event label and the run number, and our outputs inside. So for each of the segments, each file input into this stage, we get out a cal-inst file, which usually means this is a calibrated data product. But in this case, since we have skipped the photometric calibration step, the units on the detector for these files is still data number per second. So these are not astrophysical flux units. These are count rate units still. So again, you see one for each of the input rate inst files, as well as the log information that's been saved. So the ECF here is what we've established previously in the pipeline for the stage, and the log is the output of the printout of that stage. Okay, so at this time, the Eureka pipeline now no longer relies on the official JWC calibration pipeline. And for the next stage, we will be extracting the spectra using the Eureka specific functionalities. So not using the outputs from the JWC pipeline. And this is mostly done because for TSOs, there are a lot of specific toggles that we're interested in, a lot of customizations that are not currently supported by the official pipeline. So Eureka provides this separate workflow in stage 3 that converts these stage 2 files into light curve files. Right. So once again, as with all stages of Eureka, there's a control file, the ECF. And this one is a lot more complicated because there are a lot of customizable options that can be used to optimize the way that your spectra is extracted. So I'm just going to go through very quickly some of the highlights from this ECF on your own time. Feel free to look through the documentation, not only on the notebook, but of course also on the Eureka official documentation that explains in detail what all of these parameter settings mean. But in the case of this MIRI LRS slitless observation, there are a few important things to note. The Y window and X window gives you the range in pixel units that you're interested in extracting over. In the case of the LRS slitless mode, the detector image is roughly 390 pixels tall, right? And that from 0 to 390 gives you the entire wavelength range subtended by the grading. In practice, the longer wavelengths, which are at lower Y pixel values, have relatively low signal to noise, as well as some other systematics that generally make the light curves of poor quality. So for the sake of this reduction, we are limiting the range here to pixel ranges between 141 and 390, right? And this corresponds to, as you see here, the wavelength range roughly between 5 and 12 microns. So we're getting rid of the last 2 microns of the wavelength range that are of poor signal to noise. Likewise, in the x direction, we want to exclude some of the edge pixels on either end of the subarray, which are some of them are reference pixels and others are just poor sensitivity. So we've restricted our range to between 11 and 61. So you're probably not going to need to change this much. This is pretty much optimized for a MIRI LRS dataset. But keep in mind that you are able to change these if you want to, for example, expand the wavelength range. I could make this value here 100 instead. That gives you maybe another 0.5 microns in wavelength range on the red end. Some other important toggles is outlier rejection. So this FF outlier parameter does a spatial outlier rejection, a time-based outlier rejection on the background region. So when you set it to false, it only looks at pixels that are far away from the central spectral trace. But if you use true, you can actually do this exercise across the entire detector. But this is not recommended if you have very deep signals, because it runs into the problem of erroneously removing the astrophysical signal that you're interested in. So generally, in this case, you have a hot Jupiter, which has very deep eclipses. So you don't want to have this to be true, because you run into the risk of removing part of the eclipse in this outlier rejection stage. And these values give you the sigma threshold you're using to do this outlier rejection. And once again, this is done on the time axis, pixel by pixel. So what the pipeline does, it takes the time series of each pixel on the subarray and runs a outlier rejection algorithm that removes hot pixels and other spurious outlying pixel values to clean up the data set for later processing. Okay, another important parameter here is BG_HW. This is the half-width exclusion region that delineates the inner boundary of the background region around the spectral trace. So here we have an exclusion region of 11 pixels on either side of the spectral trace, beyond which we're considering all the pixels as background pixels, and inside of which we're not going to be running the background cleaning steps. So you can set this to be smaller to have more background pixels per row to use for your background subtraction, or you can make this larger to avoid more of the central bright regions. And this P3 threshold parameter setting gives you the outlier rejection threshold used during background subtraction. So sort of similar to background threshold above here, this is a sigma threshold used for cleaning the background when doing the background subtraction. And this is, in this case, this is a spatial outlier rejection algorithm. The next block here affects extracting the central spectral trace. So just like above, we have a half width that delineates where our aperture region is for spectral extraction. In this case, this is 5 pixels on either side of the spectral trace. This can be adjusted to include more or less of the PSF of the spectrum. Here we have chosen 5 pixels, which typically gives you a pretty good signal to noise, pretty optimal. But again, this is one of those important parameters that you can adjust to try and optimize how you're getting your spectrum out of the data. The next important parameter here is fit type. This is essentially toggling what kind of method you're using to construct the spatial profile of the spectrum's PSF. So this is essentially the profile of the flux along each row, the shape of the PSF that is then used to do spectral extraction. And these various, Eureka supports various ways to do this. Metadata takes the median of along the time series and collapses it to build up your spectral template. And having set med data, we are allowed to then set the window length, essentially the smoothing window in the spatial direction you're using to construct your data set, as well as the median threshold for the flagging outliers in the frame that you're using to construct your PSF model. So here we're set the window length of 7 pixels and the median threshold of 5 sigma. There are other ways to do this. There's a polynomial fit type, which we're not using, so we can ignore these next two toggles. Suffice to say, this is now the outline rejection during the optimal spectral extraction stage. So what's happening is you're constructing a PSF template for each wavelength, based in this case on the median of all of the integrations, and you're fitting that integration by integration to the flux that's measured on the detector. And this is done using a sort of a least squares optimization routine, and you can reject outlying pixels from the residuals of that fit to then refine the flux that you're extracting in a sort of iterative manner. So this is an important threshold to set. Here is set to 10 sigma, which is pretty high, but you can lower or raise this depending on the performance of your light curve in later steps. So the rest of this is kind of more metadata. This is diagnostics for how many plots you want this Eureka stage to output into your file directory. But again, so this kind of goes over some of the important parameters that you'll be interested in when customizing your spectral extraction. So having explained some of this, I'm just going to compile this ECF, which saves it to the directory, and then run it. And this stage is very, very fast. And produce a number of plots, which I'll actually look at in the directory that is created. So once again, we have a stage 3 directory with the run name. There's a subdirectory within this that gives you information about the aperture size and the background region that you use. So in this case, it's 5 pixel, half width for the aperture, exclusion region of the half width 11 pixels. So what you get is a bunch of files, and actually still running. But in a moment when it's finished, I'll go through some of the images that are produced to help you visualize what's actually happening with the pipeline in a better way. Should be done any moment now. So let's start with this plot here. So here is essentially what the pipeline is doing to determine the center of the spectral trace. So this is essentially a collapsed version of the detector in the dispersion direction. So we're seeing horizontally across the collapsed spectral trace at the center of the spectral trace region where the flux reaches its maximum. And the blue points here is the actual data. And what the pipeline has done is fit a Gaussian into this profile to determine exactly where the center is. So the green line here, the green dashed line, vertical line, is where the pipeline thinks the center of the spectral trace is. And you can see that this is doing a very, very good job. The Gaussian fit is fitting through all the points nicely. And it's very close to the brightest row, or in this case, brightest column. We actually tilted the sub-array horizontally in our visualization here. So this is now row. So this is just giving you a diagnostic of how well the pipeline has identified the location of the spectrum on the detector. And you can see it's doing a really good job. It does a fit actually to every integration. It does a Gaussian fit to the position of the spectral trace centroid in every integration, and it keeps track of exactly where it is. And this gives you essentially the jitter in the pointing of the jitter of the pointing of the telescope, as well as some other detector effects that affect exactly where the spectrum falls on the detector. But in practice, JWC is super stable. So you can see that across this segment of the time series, the centric position of the source varies by less than 0.03 pixels, right? So this is very, very, very tight, but not absolutely the same position. And in fact, this small shift in the centric position can affect the flux level due to the varying sensitivity across the subdetector. So what happens is Eureka saves this array for later use. So we can actually use the position of the centroid in time as a vector for detrending systematics in the light curve. This is a very important data set to assess how well the spectrum is steady on the subarray. Likewise, the profile width, the Gaussian width of this the source's PSF also varies a little bit in time. Again, very, very little, but nonetheless, this can be an important source of correlated noise in the final end. So I want to not go through all these, but here's another very, very nice plot that shows on the left, this is the detector image, the collapsed median frame, once again, tilted horizontally. So here, detector pixel position would otherwise be rows, but here you see them as columns. And going across here in the spatial direction, we see the variation in flux due to the source's PSF. And on the right here is a median collapsed PSF model essentially. So you're seeing the shape of the PSF as a function of pixel position in the spatial direction. You can see a very, very strong peak here in the middle. And you also have these wavy rings, which are characteristic of the MIRI LRS source PSF. So just gives you a sense of the shape of the PSF. And crucially here, you're allowed to assess how your choices for the aperture size and the background exclusion region are against the true shape of the PSF. So you see that the green region is our extraction region, which comfortably encloses most of the flux, which is good. And then the orange region tells you the inner boundary of the background region. And you can see here, it's doing a good job at excluding basically all the flux from the source. And you're really looking at regions of the detector that are almost entirely background, right? So this is telling you that these are pretty good choices. But again, you can move these green lines closer or farther away from the center of the source's PSF, depending on how you want to optimize your data set. And finally, I'm going to show you, this output. So this is actually kind of a little bit of a complicated image for people who are not used to seeing these, but this is essentially a 2D spectral image where you have on the x-axis the wavelength. Right? So this is the actual wavelength of each row on the detector as defined in the WCS step of the stage 2 pipeline. And integration. So essentially going, as you go up, you're going forward in time, sequentially through the integrations. So what you can see immediately is that you have this little region here around integration number 1500 that is low in flux relative to the rest of the time series. And this corresponds exactly to the secondary eclipse of the planet. You're seeing the planet pass behind the host star, and the flux decreases sharply and then rises again when it reemerges on the other side of the star. Okay, so I think that goes over most of the important outputs from this stage of the pipeline. So with that, we're going to proceed to the last stage of this notebook, which is stage 4. Now, stage 4 in this case is extracting the light curves from the spectral images to create the time series data sets that we will then fit in the next notebook. So in this case, we're interested only in the white light curves. This is the total flux across the wavelength range integrated together. So this is what we're doing by setting n spec channel to 1. So we're only having one spectral channel that subtends the wavelength range from 5 to 10.5 microns. Right? So we're summing up all the flux across that wavelength range for each integration and combining that into a single photometric data point that is then one of the data points in the light curve. So in principle, you can set this to higher values to then break up the wavelength array into different equal wavelength bins for use in doing, for example, transmission spectroscopy, where we're interested in the variation in the eclipse or transit depth as a function of wavelength. But in the case, for the sake of simplicity, we're just going to look at the white light curve. So we're summing up all the flux between 5 and 10.5 microns into a single light curve. So once again, there's a lot of customizable parameters here that you can toggle to adjust the way that the Eureka pipeline cleans this light curve. In this case, we are using a 4 sigma rolling median filter of width 20 data points. So for each data point, it looks at the 20 adjacent points, calculates the median and the standard deviation, and excludes those that differ by 4 sigma. Because this value can be raised or lowered depending on how aggressive you want Eureka to clean your data set. And this is then done iteratively to trim in an iterative fashion all these outliers. Another important setting is fill value. You can either choose to interpolate all those bad pixels bad data points that you've identified, or as is established here in this ECF, we mask them. So we just ignore them. And this is probably the safest choice, because you don't actually know a priori what the actual flux was during that time. And you can run into trouble if you try to have the pipeline guess what it was. So the safest option is, if the pipeline identifies an outlier in the time series, it masks them. So those points are no longer entering into the subsequent stage, the fitting stage. So again, on your own time, if you're curious, you can read through the descriptions of all these customizable parameters. But for now, we're going to compile this ECF and then run this stage, which once again will be very fast. It finished very, very quickly. So let's see what came out. In this case, we have stage 4_white for white light curve. And it has a very similar format to the stage 3 subdirectory. We have, once again, the 2D spectral image, this case trimmed to the wavelength range that we want, so 5 to 10.5 microns. And you can see, likewise, you have this nice eclipse here around integration number 1500, showing up very clearly in this spectral image. This is what we want, right? This is the white light curve. This is just one subset of the entire data set. For the sake of this webinar, we've only looked at the first 6 segments of the light curve, which covers the initial ramp. This is a systematic of the mirror detectors, not astrophysical, and goes to right after the secondary eclipse. So this is the first secondary eclipse, the phase curve. You can see very, very nicely resolved here. We have a very, very sharp ingress and egress. And you can also see that the pipeline has done a pretty good job of removing outliers. There are very few visual outliers, maybe a few left over. But again, these are things that you can visually and quantitatively ascertain from each of the extractions. You can customize the sigma threshold that you're using to get rid of these outliers. And the last plot here is the background. So it's doing a row-by-row background subtraction using the region that we established in the previous step. So you have this exclusion region for the background half width. You can see the measured background flux as a function of time. And you can see that, interestingly, it's not constant. There's a little bit of a downward slope here, but otherwise it's roughly very steady. And just like the light curve, it shows this initial ramp, which is characteristic of a lot of the mirroring TSOs. But otherwise, it's doing a pretty good job at quantifying background. In this case, we do see a few more visible outliers. So this is one of those cases where you can look at this plot and see, okay, maybe we can adjust the background threshold, the sigma clipping, to be a little bit more aggressive and get rid of some of these points. But again, the point of this background, in addition to removing the background for the flux, is for use in detrending later. So we can use this vector of the background level as a systematic that we are detrending against when we fit the light curve. So with that, we have reached the end of stage 4. So we now have a white light curve, a very nice data set that we can then pass to the fitting stages, which Taylor will now take over. But before we transition, there's this last bit of text here at the end of the notebook that kind of gives you a little bit of a recipe for how you may consider improving this extraction. So this is sorted by the most impactful to less impactful customizable options. As I mentioned, the regions that you choose for where your spectrum is extracted and where your background is perhaps have the most impact, because that directly affects the signal to noise of each point in the time series. But some of these other thresholds, like the sigma clipping in the background, signal clipping when constructing the optimal PSF fit template, and some of the other toggleable steps for doing outlier rejection also have a pretty good, pretty significant effect on the quality of the light curve that you get out of stage 4. So in practice, when you're using this on a data set that you're interested in, it is helpful to run the first 4 stages with a lot of different settings, and then compare the performance of those light curves against your fitting results. And that can steer you into some specific parameter settings that optimize the performance, right? Optimize the precision of your data set and the respective astrophysical parameters that you're inferring from the data set.